So we have about 100, 110 reactors in the U.S., and we have about 110 design permits. But with an SMR, it's the same design everywhere.
This is EnergyCast, and I'm Jay Dowenhauer. Today we're talking about small modular reactors, the next generation in nuclear technology. And if you want to skip the monologue and go straight to the interview, that begins at the 3:10 mark. I'm a big fan of nuclear, as you can probably tell. It's big, baseload, efficient, and carbon-free. You probably remember this Thanksgiving prayer from 1990.
And Lord, we're especially thankful for nuclear power, the cleanest, safest energy source there is. Except for solar, which is just a pipe dream.
Now give Homer a break, that was a long time ago. But nuclear also has a few drawbacks. It's extremely complicated to build. Probably no other project is as massive. Regulations and permits make up a lot of that. The American nuclear industry didn't do themselves any favors by making each reactor design different. You don't see a unique boiler design at each coal plant, and you don't see uniquely designed windmills at each wind farm. Uniformity helps, and to its credit, the nuclear industry has a system whereby the reactor design is pre-approved by the Nuclear Regulatory Commission. According to the NRC website, there are 6 approved designs. The one we probably hear the most about is Westinghouse's AP1000 model. Small modular reactors, which we'll be discussing today, take that concept to the next level. The entire reactor is prefabricated. It's a series of reactor modules as opposed to one giant reactor, and even its fuel is simple to extract when it's spent. The leader in this technology is NuScale. They are an Oregon-based company and last year formally submitted their reactor design to the NRC. They expect a ruling in 2020. I saved a clip from my Governor Perry episode during his confirmation hearing where NuScale was specifically name-checked as a leader in next-generation nuclear technology.
I'm encouraged to see that research is being done around the U.S. in terms of the future of nuclear energy, new technology, particularly the small modular reactors. In what ways can DOE work with the private sector? I know there are companies, NuScale Power. How can DOE further this research and speed the adoption of some of these new technologies?
My historical engagement with universities as a governor, and obviously
NuScale is currently developing its first project in Idaho with a municipal power cooperative called UAMPS. We'll discuss in my interview why Idaho may be the perfect location for such an ambitious project. NuScale is a great example of a theme I am constantly returning to, solving the negatives inherent in an energy technology. Our guest today is Dr. Joseph Smith, professor at Missouri S&T in Rolla. Dr. Smith was part of the early development team that pioneered SMR technology and today leads a group at the school called the SMR Research and Education Consortium. We covered several of the benefits SMRs can provide, as well as what I would agree is a smarter national nuclear policy. I hope you enjoy my conversation with Dr. Joseph Smith. We're here with Dr. Joseph Smith, professor at Missouri University of Science and Technology. You've worked in many fields, but I want to focus on small modular reactors. How did you get involved with SMR technology?
I worked as a group lead at the Idaho National Laboratory. In part of that group, we focused on hybrid energy systems. And so a hybrid energy system is something that combines multiple sources of energy to produce multiple products. It could be electricity, it could be chemicals, it could be heat. And so as part of that hybrid energy system research, small modular reactors fit in very nicely because it's a carbon-free energy source that provides an excellent heat source. While I was at INL, we developed several process models to analyze the effectiveness of these SMR reactors. Since that time, we've been focused on that area, and we've been doing the same thing at the university. We've published several papers. We're actually working on a book related to this technology.
Small modular reactors. I believe one of the benefits of conventional nuclear is its size and its ability to create a lot of energy. So I think the most basic question might be, why go smaller?
There's two real main reasons. One of them has to do with inherent safety. All of the reactors we have in the U.S. and most of them in the world are light water reactors, and they operate at a certain temperature. And we've seen unfortunate events like Fukushima that are related not necessarily to the nuclear side, but there's some safety issues, and a lot of people are concerned about that. So small modular reactors are next generation, they're new design, and they're a much safer reactor because of the passive cooling systems that they involve, and so they allow us then to improve the safety. The second reason is because of modularity. The AP1000 is about 50% modular. That means that you build pieces in a plant and then you ship them to site and you assemble them like Legos. A small modular reactor, by comparison, is 100% modular. It can be fabricated under well-controlled machining and quality control in a plant and then shipped to site. And you couldn't do that with a large reactor just because of the size and the weight and all the logistics associated with it. Another benefit is not necessarily the driver for making them smaller, but another benefit is the risk profile. When you build a big reactor, you're talking of billions and billions of dollars. But for a company like UAMPS that is funding the next project we expect to see in Idaho with a small modular reactor, the risk profile is a lot smaller, and so you can get a reactor in the ground producing electricity a lot faster. You don't wait 10 years to get the first megawatt of electricity out.
In what ways are SMRs more efficient than conventional nuclear reactors?
One of the things that you can do with an SMR, because it's smaller, is that you can keep them online longer. A large plant has to go down about every 18 to 24 months to do a fuel changeout. The NuScale reactor, for example, actually has multiple canisters. They are able to take one of them offline, so instead of shutting down the plant while they do refueling, they can do that continuously without affecting their power production.
In what ways are SMRs safer than conventional nuclear? What is inherent in their design that makes them safer?
Right. One of the big concerns that people have, because they hear about this in the news, is the meltdown. They think about Chernobyl, they think about Fukushima, they see these pictures in their mind of these reactors that are overheating and they're melting the containment. So by comparison, an SMR have a way that the reactor can actually shut down if they were to lose, like Fukushima did, the external cooling pumps. The reactors themselves can dissipate the heat and shut themselves down without human intervention. The other thing about an SMR, the core is small enough and the containment is small, it's underground. So you don't have this concern of like somebody driving an airplane into the containment vessel, right? And then the last thing is because it's smaller, it's more compact, it's got this passive cooling system, the emergency zone around the reactor is much smaller. A large nuclear reactor has a fairly significant miles EPZ, whereas a small modular reactor will have maybe tens of acres for an EPZ. So it's easier to protect. The security issues associated with that are not as complex as a large plant.
Can SMRs replace nuclear reactors at brownfield nuclear facilities?
Yes. In fact, the concept of putting an SMR into a brownfield is actually one that's been studied and has shown a great promise. Not just an existing large nuclear reactor, but coal plants. Because the SMR, again, is designed to generate heat, just as if you were burning coal or gas. There's some upgrading because these have to be nuclear-grade materials. But all of the heat transfer equipment, handling the power and transporting it out already exists. And so that is another opportunity to retrofit, as it were, either a brownfield nuclear site where you have an old reactor and you now replace it with a new modern SMR unit, or a coal plant. Actually, there are a lot of coal plants that have retired in the last 10 or so years, so there's a lot of opportunity there as well.
You said you got involved because you were trying to find ways for SMRs to do a lot of jobs. SMRs can also easily be converted for other uses than electricity at the same facility. Tell us how that works.
Companies like Exxon, ConocoPhillips, right now, when they process crude, they burn natural gas or some type of a hydrocarbon to generate the heat that's required to distill this crude down into gasoline and jet fuel and diesel and so forth. And so one of the scenarios we actually looked at is how can you use nuclear heat to replace that carbon heat? Same thing with chemical plants, other types of industrial facilities that require heat. Another thing that we actually looked at in terms of hybrid energy systems of combining a nuclear plant with a gas-fired plant, with a solar farm, and with a wind farm. And you would use that heat from a nuclear plant then to run some type of a renewable source to generate some chemicals that you could then turn into a transportation fuel. So in effect, you're storing that renewable energy with nuclear energy and putting it into a liquid fuel that can be shipped around.
I'm a project manager by trade, and I love talking about nuclear projects because I don't think there's anything something else that has a longer timeline, let alone other energy sources. How can SMR technology reduce those timelines compared to what it would take to build a conventional plant?
The main way is that, again, modularity. To build the first one, there's no time savings, right? Because it's kind of a first of a kind. But once you get into production, it's the same design everywhere, as opposed to the current reactors that are design site specific. So we have about 100, 110 reactors in the U.S., and we have about 110 design permits.
It seemed like before Fukushima that we were going to see a lot more nuclear builds, and we also heard a lot about pre-approved designs for nuclear reactors. How would that have compressed project timelines?
What you're talking about is the licensing phase of a project, and that typically can be 5 years, as much as 10. And so if there was any way to shorten that design phase, that would certainly shorten the time for large or small. One of the challenges for doing it for large is that there's a lot of uncertainty in the design because of site specifics. But with an SMR, because it's the same design, they issue a design permit, and now that's good for the different places that you want to place that specific design. But if you can decouple that specific reactor design from the site issues, then that can shorten, probably not so much for a large one, but certainly for an SMR.
People have a lot of questions about the fuel used for nuclear technologies, where it comes from, how it's transported, what happens after it's spent. Take us through the life cycle of fuel for an SMR.
Sure, you bet. It's a uranium base today. It starts as what's called yellow cake, the uranium mineral that is mined. They bring it out of the ground, and then they process it, and they come up with a uranium fuel, and then they can enrich it, and they come up with a fuel that can go into a fuel rod that is then shipped to site, where that becomes the active ingredient of the core. As you put that fuel rod into the core for approximately 16, 18, 24 months, anywhere, it can go from a year to 2 years, basically just consuming the radioactivity of the fuel. And so once it's burned to a certain level, then they extract that and they store those. Those are the, quote, waste, but it's stored actually on site. And at some future day where they change the reactor type, where it allows them then to burn that, quote, spent fuel, they actually can extract additional power from that. Even though we call it spent fuel, it's probably one of the largest concentrated energy sources in the world. Right now, the SMR reactor burns fuel that has about 19 or so percent fissile uranium in order to operate. And so that's the life cycle of a fuel element from the ground to the site and then storage.
It seems to me that you definitely have some opinions about what should be done with the spent fuel. I've never understood the fear about moving the fuel around to be recycled. They have to get the fuel to the plants after all. Why couldn't they just deadhead back with the waste, right? Let's pretend you're completely in charge and have final say. What would a safe, reliable recycling program look like in this country?
The French have probably got the best model of that, and they have a centralized site, and they collect that. I really do support a centralized collection and storage site that you can then manage and maintain and oversee. Now, how do we get it there, right? As you mentioned, you're already transporting the rods to site, but now you're just basically doubling the transport. One of the policies that I would be in favor of is once you get them to site and evolving the technology that allows that fuel to be burned and the volume of that fuel to be reduced to a level that then when you transport it back to a centralized storage location, the amount is much less. That's a long-term vision, and it's not going to happen overnight, but that's something that we should be moving toward because I think that's the right model.
Let's talk about commercialization and where these companies are. NuScale is really at the forefront of SMRs. They have a facility they're planning in Idaho. What's left for them to do at this point to get going?
So one of the challenges is that first of a kind. Building the very first one is a big challenge, but NuScale has submitted and been approved by the NRC, and so they have a design package now. They have a group of companies, the UAMPS, that are funding this project. Fluor is one of the main companies that is putting money in, and so they'll build that first one there in Idaho. Once it's in the ground, then a lot of the questions that you've actually asked me today in terms of manufacturing, safety issues, efficiency, all those questions get answered. NuScale is a great company, and they've got a very innovative staff staff that have worked closely with Idaho National Lab. Idaho National Lab is the Department of Energy's nuclear lab, and so it makes sense that it would be built in Idaho, where they've built about 50 or so other types of reactors in that same area. I'm so excited to see it actually go on the ground.
That gets us to your Small Modular Reactor Research and Education Consortium that's been organized at your school. Tell us about that partnership and some of the work you're doing there.
The idea is to bring industry closer to academia, and so that we can leverage the resources that are in a university setting with industrial needs and provide a mechanism to transfer that technology back to industry. We've done work on things like we actually studied the supply chain for an SMR reactor industry and identified the potential economic impact for an SMR industry in the Missouri Midwest region. And it's pretty significant in terms of all of the jobs that are associated with that supply chain in providing and producing SMRs. We also did work in areas like hybrid systems. We have an aluminum smelter in Missouri. Noranda operates this, and making aluminum takes a lot of electricity. And so combining a small modular reactor with an aluminum smelter actually reduces the production costs, increases the environmental performance for aluminum smelting. And, Ameren is our local electricity provider. Westinghouse was our nuclear company that we're working with. Again, it's combining academia with industrial need.
One of the things I love talking about with a guest who works in a region I'm covering for the first time is learning about the advantages a region has that are unique to them. Tell us about what strengths Missouri has developing this energy sector.
So we have a couple things that make Missouri kind of unique. One of them is we have good transportation out. We have two big rivers, the Missouri River and the Mississippi River. And so in terms of shipping things, being able to ship it on barges is a really big deal. The other thing is we're kind of central, right? And so getting us out into other parts of the country is a lot easier than whether it's a West Coast or East Coast type of an industry. The other thing that Missouri has, there's a tremendous industrial base in the Midwest in terms of energy. So it fits into that area very nicely.
And finally, I'm going to finish with a lightning round of your thoughts on different energy technologies, starting with natural gas.
Natural gas is exciting because you can get a plant in the ground for very low cost and you can start producing electricity very quickly. It's cleaner than coal. It's got some challenges, but I completely support natural gas.
Crude oil.
Crude oil is something that we need. It's hard to have an electric airplane. We can certainly have electric cars, but we will always need liquid fuels. And so crude oil is a necessity in our society.
I'm now at nuclear. I'm going to break this apart into two kinds. Conventional nuclear, thoughts?
Conventional nuclear has had its place in our history. I believe that nuclear will be part of our future, but I think it's going to be next generation. You'll see nuclear energy evolve.
And then the second part of that, SMR, their place in the portfolio.
And SMR is part of that evolution process, making things smaller, more efficient, reducing risk. And so SMRs themselves will evolve from light water to salt reactors and so forth.
Coal.
We got a lot of coal in the world. It's the cheapest form of energy we have. It's the dirtiest form of energy we have. But for me to tell people in Africa that go to bed every night with no electricity that I'm sorry, you can't burn coal, it's not right. And so I think that coal will be part of our future as well. I don't think we have an option. And so we just need to make it cleaner.
Wind.
We'll have more wind. You've seen the reduction in cost for wind energy, and we'll continue to see a reduction in cost for wind energy and other renewable sources.
Solar.
Solar falls into that same category as wind. You've seen a significant reduction in cost of solar energy. The challenge with solar energy, again, is with wind. It's not constant, it's intermittent, and it's not transportable. We need to find ways to make those things more continuous, and that's battery or energy storage.
Biofuels.
Biofuels is a sustainable, renewable source. We don't want to burn our food, but there are ways to use cellulosic materials or other types of waste products as biofuels. Algae certainly is a great opportunity going forward, but there are some challenges, but I see more algae in biofuels.
I was wondering what you'd say being in the Midwest like you are with that one. Hydrogen fuel cells.
Fuel cells are an interesting idea. I think that they have a place in more of a niche. I don't think that we'll see large-scale fuel cell application. I do know that we'll have fuel cell cars, hydrogen fuel cells in cars. And in terms of large-scale energy production, the cost is still too high. Maybe in the future we'll see some reduction because of material science. But for now, it's pretty expensive.
Hydroelectric.
We in this country have harnessed most of all the hydroelectric opportunity. The areas I could see us finding more hydroelectric energy is in low-head hydro. You don't have these large dams like you do on some of the Colorado River dams and so forth. But yeah, hydro I think is great. but I think in our country we've harvested most all of the hydro that's available.
Geothermal.
Geothermal is one of those areas that we have started to develop. I don't know that there's a lot more that we're going to get out of geothermal in this country. There are places in the world that you'll see more geothermal energy. Shallow wells possibly will see more, but the efficiency of those geothermal systems are fairly low compared to other energy sources. So the economics are against them.
Electric vehicles.
We're going to have more of them as we see battery technology continue to evolve. Just as solar technology has evolved and wind technology has evolved, we'll see more electric vehicles.
And finally, nuclear fusion.
Nuclear fusion, going to happen. I have a good colleague of mine that says never going to happen. I don't agree with him. I think that we'll see fusion reactors in our lifetime. Lockheed is working on this technology that they claimed that they'd have a 10 megawatt unit pilot scale in the next 5 years. We'll see if that's true. I believe we'll see fusion in my lifetime.
All right. Dr. Joseph Smith, thank you so much for your time.
You're welcome, and it's good talking to you.
That was Dr. Joseph Smith, professor at Missouri S&T University and lead on the SMR Research and Education Consortium at that school. Oh, and by the way, Dr. Smith got his undergraduate, master's, and PhD all at Brigham Young, and I had to ask him what it was like going to that school with a name like Joseph Smith. Special thanks again to Dr. Smith, as well as some folks over at NewScale. All guests are sent a copy of the raw and finished product the week of release. Music was produced by Sean Stroop at Stroop Loops. You can find us at Host Energy on Instagram, and be sure to check out energy-cast.com for some great pictures and presentations going in depth on this technology. That wraps up episode 16. Be sure to join us next week when we head to the coast to talk about the future of wave technology. I'm Jay Downhauer. We'll see you next time.